Question number 7 starts off with, if the square root of k is an integer, which of the following must be integers? So you're dealing with some of your number sets. You have to know what number sets you're working with. I didn't really describe what integers were, but these number set integers have to be things such as -3, -2, -1, 0, 1, 2, and put the dots in the front or the dots in the back, which means this list goes on forever. It's an infinite set. What you notice is that there's no fractions, there's no decimals, so it's all the whole numbers and their opposites. So if the square root of k is an integer, we've got to go back and think about what the square root does. So I'm going to ask you to think about what numbers are perfect squares, because if we take the square root of perfect squares, we get integers. So that's the point I'm trying to make here. Perfect squares, 1. 1 times 1 is 1. 2 times 2 is 4. So I'm generating this list of perfect squares. 3 times 3 is 9. 4 times 4 is 16. These numbers back here are referred to as perfect squares by the geometry of a square that has dimensions of 2 by 2 or 4 by 4. So we can generate an infinite set of perfect squares. Well, if we take the square root of k and it comes out to be an integer, what we're saying is that it had to be one of these perfect squares. So with that being said, what we can do is we can start evaluating some of these ideas. They say the square root of k over 4. Now there's some radical rules here that we could also get into. It says the square root of a quotient is the quotient of the square roots. So in this problem, the square root of k over the square root of 4. Which means we could rewrite this as the square root of k is going to be an integer all day long. But the square root of 4 is going to be a 2. Now k can be any one of these perfect square numbers if it's going to be an integer. If I took every one of these perfect square numbers and divided them by 2, would I always get an integer? Well, here's a counterexample. If I take 1 divided by 2, it is not an integer. So here's a counterexample. It will not always be. And that's just one example if I use the perfect square of 1. Any of these that are not even would be a counterexample. So I know that that one is wrong. So we're not going to use that one. The next one says the square root of 5k squared. Well, what I do know is that squaring undoes a square root. Squaring fundamentally is the inverse of square rooting. So if I square a square root, I'll just be left with 5k. And the square root of k is an integer, which basically says I just got k that can be any one of these perfect square numbers. And if I take 5 times any of those integers of perfect squares, I should always get another integer. And that seems fairly reasonable. 5 times 1 is 5, 5 times 4 is 20, 5 times 9 is 45. I'll always get one. So I want to keep that one. That should always be a integer as well. I've got to evaluate the next one. So the square root of 9 times k. There's a property of radicals that says the square root of a product is the product of the square root. So I can break this up into the two square roots of square root of 9 times the square root of k. The square root of 9, I guarantee, is 3, because the square root of 9 is a perfect square, 3. And the square root of k, they already guaranteed us, is an integer. So if I take 3 times another integer, will it always be another integer? Well, I believe that's going to be true because it's going to be taking 3 times 1, 3 times 4, 3 times 9. Every one of those is going to be an integer. So when it boils right down to it, the statements 2 and 3 are both going to be integers guaranteed. So look at my answer choices, 2 and 3 only. So let it be.